Yeah, good evening, one and all. Mm, Today I'm going to share this 1 minute. Yeah, in previous presentation, I have started groundwater exploration. What is groundwater? So, what is hydrology, hydrological cycle, and all we have covered in previous presentation. Now, today I'm going to cover this block 2 groundwater exploration. In the block 2 groundwater exploration, we are going to cover geological exploration, geophysical exploration, and remote sensing and GIS applications in groundwater exploration. So, try to cover the previous presentation. Try to watch that previous presentation. Then you will know the detailed hydrological cycle and groundwater exploration. So now, uh, see here you can observe that in groundwater exploration, water is a vital for development and industrial growth, particularly where surface water is scarce. Growing population and demands for irrigation, domestic and industrial use have strained water resources. Groundwater exploration is essential for effective and sustainable water management. Proper exploration techniques are crucial from a source location to well design and construction. So, in groundwater exploration, these are the main important uh, techniques that are exploration and this and the source location, locating the source and well design and construction is the most important parts in the groundwater exploration. Oh, sorry. Here you can observe that in groundwater where it occurs and what are the aquifers I have discussed in the previous hydrological cycle presentation, that is block 1. Now we can just recollect here also that groundwater occurrence and aquifers. So groundwater is found in permeable geological formation. Geological formation which may have groundwater is called as the aquifer. So known as a aquifer. So aquifer is nothing but a geological formations which may have the groundwater and it permits to the wells. So aquifer means it has to hold the water and it has to permit the water to the exploration wells. Yes. 1 minute. Thank you for hold. Okay. In groundwater occurrence and aquifers, groundwater is found in permeable geological formation known as aquifers. So aquifers, nothing but a geological formations which may hold water and permit to the exploration well. Aquifers includes unconsolidated rocks, clastic sedimentary rocks, volcanic rocks, and crystalline rocks. Aquifers may be a geological formation that are sedimentary rocks, volcanic rocks, or crystalline rocks, or any basaltic lava flows and basaltic rock formations. So any rock formation that holding groundwater means it is a aquifer. But it should hold the water and it should release or permit or it should have permeability to allow the water to the exploration well. So whether it is a sedimentary rock or volcanic rock or any crystalline rock, whatever. So and intersect with the aquifers such as capillary, subcapillary, and supercapillary capillary spaces enable groundwater movement. Intersects within the aquifer. Within the aquifer, there may be a pore spaces, there may be a cementing material. So these pore spaces are these empty spaces filled with water, and it may have such capillary and subcapillary or supercapillary spaces enable groundwater movement. Here you can observe these are the aquifer, unconfined aquifer. This is the confined aquifer, and these two borewells are located or capturing the water from the unconfined aquifer, and this borewell or this open well is capturing or taking water from the unconfined aquifer. This is the unconfined aquifer water table, and this is the this line. This is the confined aquifers water table. So here this well acting as a flow artesian well because of this this confined aquifer located borewell groundwater table is above the borewell surface or surface of the earth. Here also artesian well, this surface, water table, uh, water table crossing the surface, earth surface elevation. Here it is this borewell crossing the and above the earth surface, and it is below the actual water level of the confined aquifer. So that's why it is without borewell or without bore motor, it is flowing. That's why it is called as flowing artesian well, because this confined aquifer water level is higher than the this borewell surface or top. That's why this water coming through the borewell without pumping. Here you can observe this is the natural stream, and these are the water table of the unconfined aquifer. Here you can observe. If you observe water level in this well and this well, this is higher or near to the surface, this water level, whereas in this well, it is the lower to the actual earth surface. So that's why we can say this well is capturing from unconfined and this is capturing water from confined aquifers. 1 minute. Okay. Next, here you can observe distribution of groundwater and geological formation. Geological formation or an aquifer which is holding the groundwater. So, what is the distribution of groundwater in the geological formation? Geological formation, nothing but aquifer. So, this is the unsaturated zone. This is the earth surface. You can observe this is the earth surface, and this cross section is unsaturated zone or unconfined zone. And in unsaturated zone, pore spaces are filled with air and some gaps are filled with water. So, whereas in Confined aquifer or saturated zone, total pore spaces are filled with water only. So, above the water table, we'll find the unsaturated zone. Below the water table, uh, we find the saturated zone. So here you can observe this from saturated zone below the water table. This well is capturing the water, and you can observe how pollution will be there from the surface, from infiltration or leaching process. It will reaches the groundwater table. So this groundwater may be contaminated with the leaches or effluents which are coming from the industries or urbanization. So it may reach the groundwater table through the leaching process or in infiltration process, and it will contaminate the this plume. You can yellow color or light greenish color plume, you can observe this is the pollution zone. Like this, in subsurface, we can find a distribution of the groundwater in geological formation or in the aquifers. So here, groundwater occurrence varies across geological formations. Aquifer types include alluvial valleys, tectonic valleys, abundant or buried valleys, and extensive plains with unconsolidated sediments, and groundwater in lithified, sedimentary, volcanic, crystalline, and metamorphic rocks contributes to water resources. These all type of rocks contributed to water resources through the porous media or fracture zones or weathering zones. So, so distributes the groundwater distribution in the aquifer system. Here you can observe methods of geological exploration. So when we talk about groundwater exploration, we have studied aquifer system, hydrological system, how aquifers will be, type of aquifers, how aquifers will form, and how aquifers will act according to the water table and pore spaces. Now we are going to discuss what are the methods of exploration of groundwater. So here, first we are discussing about methods of geological exploration. Next, we are going to discuss about geophysical exploration, and next, we are going to discuss about this seismic reflection and refraction methods. And next, we are going to discuss about understand the remote sensing and GIS in the identification of groundwater resources. So, like that, we are going to cover in this presentation different type of explorations, groundwater exploration methods. Okay, now the method first we are going to discuss about the geological groundwater exploration. Here you can observe before going to uh, read this text. Here you can observe that this is the one of the GIS prepared map. It is called as groundwater potential zones. For for prepare this groundwater potential zones. Groundwater potential means where groundwater may available, and according to the geological rock formations, structural factors, lineaments, drainage, slope, all these geological, geomorphological, and structural all factors we have to consider, and we have to take their values, and we have to prepare this potential zones, groundwater potential zones. So where groundwater may available in higher quantity. So in the here you can observe that this blue indicate excellent potential zones in the in this map. Western side or eastern side or northeastern side, blue zone is having more, because in this zone we are having groundwater potential zones. If you drill in this area, if you drill in this area, you may get groundwater. So if you drill in this red color or in greenish color, you may not get sufficient water. Whereas in this light bluish color, you may get moderate to good potential zones. Like that, geological aspects are, or geological all factors are controlling the availability of the groundwater. That's why we have to study geological factors before going to groundwater exploration. So for for prepare this single map of the groundwater potential zone. This is a single map, but it may include the all the geological factors like slope of the area, drainage system of the area, geological formations of the area, rainfall of the area, and infiltration rate of the area, soil type of the area, the lineaments of the area. All factors include in the single groundwater potential zone map. So, after taking all the geological factors uh, readings only, we can prepare a good groundwater potential zone map. It may help this map, it may helps in the explore the groundwater, where we can drill and where we should not drill. Like that, we may get some idea regarding the particular area. Now, various methods are employed for geological exploration, including aerial photographs, structure analysis, geomorphological studies, well inventory, geological mapping, test drilling, geological logging, test pits and auger drilling, and continuous core penetrometer, and each method aids to assessing groundwater potential and contributes to effective management. See here, we have to consider all these factors like geomorphological studies, structural studies, and aerial photographs, and existing borewells lithology, and geological logging, and drilling test, pits, auger drilling, like that, all factors we have to consider before going to the groundwater exploration. These are the geological factors which may which may give the complete information about potential zones of the groundwater of particular area. And next, we are going to discuss this geophysical exploration methods for groundwater exploration. So here you can observe this. These are the syscall resistivity, multi-electrode resistivity meter, and uh, from these resistivity data, we can prepare a pseudo section of the larger areas we can. Whereas in restivity methods, particular in a Schlumberger restivity method, we'll get only point data, but whereas in multi-electrode restivity meter methods, we'll get large or more mm, more area or large area we can cover with the multi-electrode restivity imaging. And where you can see here, this is the restivity well logging method, and this is the where well logging data interpretation. So here, geophysical methods are crucial for uncovering subsurface secrets. Importance includes locating aquifers, estimating depths, and identifying geological structures, and overview of gravity, magnetic, seismic, and electrical methods, with emphasis on electrical for groundwater studies. Explanation of groundwater movement in rocks under pressure gradients. So, like this, number of geophysical methods are there: gravity methods, magnetic methods, seismic method, electrical resistivity methods. So, these are the comes on the geophysical exploration or geophysical methods for exploration of groundwater. Ah, later, we'll discuss about in detail in the each geophysical method. Here you can observe this is the geophysical logging in Mangochi, some area, and this is the geophysical logging data curves. See here, in electrical resistivity methods, electrodes and currents and resistivity is the ma- main properties. See, electrical resistivity method is fundamental in groundwater exploration. Resistivity defined as a material's resistance to electrical current flow, and setup involves four electrodes and calculation of apparent resistivity and into Venner array and Schlumberger array configurations. And when we talk about the this Schlumberger and Venner array electrical resistivity method, it includes the four electrodes, two are current electrodes and two are potential electrodes. We will measure the potential difference created by the electricity in the subsurface. So normally when we conduct Schlumberger or Venner resistivity methods, we will send current to the subsurface and will identify the or we will measure the difference of the potential difference will measure while sending the current, how much potential difference is creating in the subsurface will calculate. So like that we'll conduct Schlumberger and Venner methods for groundwater exploration. Particularly for groundwater exploration, borewell's location, Schlumberger method is very suitable. And when we talk about electrode configuration and sounding curves, here in resistivity survey, what we collect is uh, apparent resistivity of the subs rock formation. So apparent resistivity, where in the field we will collect only apparent resistivity values. These apparent resistivity values, when these values are matched with master curves, then only we'll get true resistivity of the particular rock formation. Then only we can decide whether it is suitable for groundwater exploration, whether these aquifer having water zones or potential zones. We can identify based on resistivity and conductivity properties. So now the electrode configuration and sounding curves. So here detailed exploration of two electrode array and dipole array configurations and sounding curves reflect geological structures and resistivity variations, and visual representation of Venner array setup with equi-spaced point electrodes, and illustration of typical sounding curves during geophysical explorations are we'll discuss in the configuration and sounding of resistivity curves. And whereas in curve matching technique, as I told in the this slide, starting uh, when apparent resistivity values are matched with master curves, then we'll get the true resistivity of the formation. Insight into direct and partial curve matching techniques for resistivity interpretation. Interpretations of two layer, three layer, and four layer field curves using master curves and auxiliary charts, and demonstration of interpretation and through practical examples. So, after collecting data, we have to calculate resistivity and we have to match with master curves, whether it is two layer or three layer or four layer. We have to identify, then only we'll get the particular thickness and resistivity of the true resistivity of the subsurface or geological formation. So what we'll do, just I will repeat again, in electrical resistivity, we'll conduct electrical resistivity methods like Schlumberger or Venner methods we'll conduct. In that, we may use four electrode methods normally. So two are current electrodes, two are potential electrodes, and in rest with resistivity meter, we will identify or we will collect the data which is created potential difference of the subsurface. After sending the current, it may create the potential difference in the subsurface formations. That potential difference we will calculate and uh, will identify the apparent resistivity of the area. This apparent resistivity area will plot in the as a curves, and these curves, apparent resistivity curves, will match with the master curves. Then only we'll get to true resistivity of the particular rock formation or subsurface of the that particular area. For this curve matching, and how many layers this subsurface is having, we'll identify with according to the thickness. So interpretation may include whether it is two layer, three layer, or four layer. We'll identify, and according to that layers thickness, will get the resistivity of the each layer, and true resistivity of the that formation. With that only we can identify the potential zones of the or conductivity zones of the groundwater, uh, groundwater or potential zones, groundwater exploration zones, or groundwater suitable drilling borewell equations. Here you can observe this is the multi-electrode resistivity method. Whereas in here, if Schlumberger Venner, we are using four electrodes, but here this tomography or imaging, resistivity imaging, we are having a number of 24 to 48 electrodes. We will conduct resistivity at a time. So with this all electrodes data, we can create a image or topography or tomography of the subsurface of geological formation. See here that behind the subsurface, electrical resistivity tomography, overview of ERT, electrical resistivity tomography as a cutting edge subsurface imaging technique. Exploration of setup with multi-electrode arrangement. Here we will get multi-electrodes. Number of electrodes will be there. You can observe in this picture. Whereas in resistivity of Schlumberger and Werner resistivity methods, we will have four electrodes. So here multi-electrodes arrangement and data acquisition system, and importance of precious data collection and processing for capturing resistivity variations. Introduction to resistive in software for generating resistivity pseudo sections, and here you can see, I will show these are the pseudo sections. So number of electrodes data will collect, and will prepare the pseudo section or subsurface cross section of the resistivity data. That is called as pseudo section, will prepare. The pseudo sections and inverse modal resistive sections will prepare. So these are the inverse pseudo section of the inverse resistivity cross sections of the subsurface geological formations of the particular area. Now here you can observe that Here you can observe these are the pseudo sections which are prepared by the tomography or multi-electrode resistivity meter. So here you can observe this dark color indicates the high resistivity zones, whereas these light colors near to the surface are low resistivity zones. See here also you can find these are the low resistivity zones. Here you can find these are the low resistivity zones, and these are the high resistivity zones. Okay. Like if we get any low resistivity zone here, like this, if we this low resistivity zone, if it is extended to deeper and deeper, here we can suggest borewell according to the depth. So it is near to the surface means it is not recommendable. But if but this lower resistivity zone, if it is extends to the deeper and deeper depths, There we can suggest the drilling of borewell with this tomography imaging. And here you can see this is the Schlumberger resistivity uh, currents, current flow, and these potentials flows, current and to the earth. Okay, these are the um, curves and voltage curves which are created in the subsurface of the earth while sending or when sending the C1 C2 current into the subsurface using the batteries. Okay, using the DC batteries. Okay, here also you can Werner array. See, all electrodes are spacing in same distance. Four electrodes are there, A, B, and M. And A and B are the current electrodes. M and N are the potential electrodes. Here, P1, P2 is the potential, and C1, C2 the current electrodes. So here, equal distance is there in the Werner array. And Werner and Schlumberger, so in Schlumberger resistivity survey, will get particular point data, vertical or subsurface data. Whereas Werner will get profile data of the particular geological formation. And this is the resistivity formula, and V and I will collect, and then we will get the apparent resistivity. Apparent resistivity only will get in the field itself. Okay, after this data matching with master curves, we will get type of A type or H type or K type or Q type curves, or combination of curves we will get. So that after matching with master curves only we will get the true resistivity of the particular geological formation. See here, this is not. mm, Presentation, you can go for me. Oh, sorry. Some disturbance is there. 1 minute. Where is that curve? Okay. Okay. See, okay. Now, since we are discussing about resistivity in geophysical methods, we have completed resistivity surveys. Now we are discussing about seismic wave types. The Understanding the wave behavior. Seismic waves play a virtual role in uncovering subsurface structures. Body waves, compressional or P waves or shear S waves, like and surface waves, religious waves, and low waves. Reflection and refraction. These are the body waves, and these are the S waves and P waves. These are the body waves, and these are the low waves, and these are the surface waves. Here you can observe in seismic waves, it works on reflection and refraction properties, like reflection coefficient influences wave amplitude and material boundaries, whereas refraction coefficient describes angular deviation at material boundaries. So reflection, it gives amplitude, and refraction, it gives the deviation at material boundaries. Understanding the critical angles is crucial in seismic refraction surveys. See here here we are creating some waves with a hammer and plate, and after these waves, when they touch the bedrock, this is the sediment and or weathered zone, whatever, and when they hit the bedrock, it will reflected and it will reaches the subsurface again, and these geophones which are placed in equal distance, it will receive the seismic waves and it will connect to the seismograph. So like that, we'll create waves and we'll send or create waves and we'll record the reflection of the seismic waves. And it will in seismograph it will create the and graphs according the bedrock bedrock orientation, bedrocks uh, structural controls like fractures and faults or any gaps in the subsurface, any fluid in the subsurface, we can find with this seismic reflection method. And when we talk about this understanding remote sensing and GIS, fundam- 1 minute. A understanding the now we are understanding the remote sensing and GIS techniques which are useful in the groundwater exploration. Here, what is GIS and what is remote sensing? We are going to discuss. Now, the fundamentals of remote sensing and GIS is remote sensing is a collects information without physical contact. In remote sensing, it will collect the information about the different type of the objects without physical contact. In GIS, it assembles, stores, manipulates, and displays geographically referenced information which is collected from the remote sensing method. And the purpose is it includes identifying ground features and analyzing hydrogeomorphology. So, in remote sensing, we are collecting data of the different terrains or different objects without physical contact. These data we are going to interpret in the GIS. In GIS, we'll assemble, store, and manipulate and display geographically referenced information. And after that, we can identify the ground features and analyze the hydrogeomorphological, or any potential zones we can identify with these two methods, a combination of remote sensing and GIS techniques. Here you can see the what is GIS. See in GPS, in, in GPS uh, and in satellites, and this is the data, software, analysis, maps preparation, and careers. So these GIS includes these type of all activities. Then only we'll get accuracy data in the apps or in the map display, GIS portable, GPS portable systems. అంతే తక్కువ రేటింగ్లో వినబడుతుంది. ఇంకా తగ్గి తగ్గి. Like this, like this, we are 1 minute. Share, okay. So like this, we are use the remote sensing and GIS application in the groundwater exploration. Here you can observe this. We will create vector data with and streets and parcels. Then we will use land usage, then elevation, then finally we'll create this real world with remote sensing and GIS techniques. Then only we'll get a large number of data or and major scale or and, most of the area we can cover with these methods. So these are the steps included in the remote sensing, like source is our sun and atmosphere in interaction, and target. This is the target or object, and it will this the reflection will identify and will store from the satellites. Then the satellite sensor transmission and these receivers and it will process in the unit system and information it passes to the our human system, and we can finally create the one useful hydrogeological or geomorphological map of the particular area. So from here to map, it is includes number of methods and a number of parameters. Number of parameters we are number of parameters includes. Next, see here with the help of remote sensing and GIS in groundwater potential zone identification, we are going to prepare this groundwater prospecting map, that is groundwater potential zones map of the particular area. Here, with this GIS and remote sensing techniques, enhancing groundwater, enhancing groundwater exploration with technology, and role of remote sensing in identifying indicators and analysis with GIS tools, and digital enhancement of remote sensing data, and integration with field studies for validation and program genetic modeling. Like this, for any particular area, we'll take remote sensing and GIS applications uh, usage and support. Then we'll create the groundwater potential zone map of the particular area. Here you can observe very good groundwater potentials are observed in the northeast or eastern part of the study area, and whereas poor groundwater available zones, potential zones means nothing but is the groundwater available zones we'll find in the south and western part of the study area. Whereas in this yellow color indicates moderate groundwater availability, and this light green indicates the good groundwater availability, whereas this blue color indicates the very good groundwater availability zones that are potential zones. Like that, with the use of geological and geophysical and remote sensing and GIS applications are with these softwares and data, it will help in the creating the groundwater potential zones. Then only we can suggest any groundwater exploration bore wells in the particular area. If you suggest in this red zone, you may not get groundwater. If you suggest in the this blue zone, we will get the groundwater, plenty of groundwater availability there. So that's why To prepare this prospecting map or potential zone map, we have to take the support of geological, geomorphological, geophysical, and remote sensing and GS techniques. So these tools are helpful in the preparing the groundwater potential zone maps, which are helpful in the groundwater exploration. So like this, I hope you understand this presentation. Try to watch number of times. You will get more clarity on this. So 1 minute. Here I can. Okay. Thank you, and thank you, sir. Uh, so try to watch previous presentation and this presentation, uh, particularly in the hydrological cycle and groundwater exploration. These two presentations give clarity. So try to watch number of times. Thank you. And have a nice day. Thank you.